Okay, thank you very much. So the next speaker is Dr. Mahmood Roshan talking about dynamical friction spiral galaxies. So please go ahead.
Hello, everyone. Do you hear me?
Yes.
Yeah, I'm grateful to organizers for inviting me to this meeting. My talk is based on these three papers. As you see, my collaborators are Sohrab Rahwar. Please let me open my webcam first. Sorry. Yeah. Sohrab Rahwar is my collaborator here, and the other collaborator is Neda Ghafourian, a postdoc in Ferdowsi University, and my former PhD student, and also Shahram Abbasi from Ferdowsi University. So this is the outline of my talk. I first give a brief review of dynamical friction and its consequences. Then I review the fastbar tension in lambda CDM. And as a proposal to solve this tension, I will talk about two types of modified gravity theories. And to see the effect of dynamical friction in these theories, I use some n-body simulations. I will present the results and will focus on the dynamical friction role in the simulation. So as you know, dynamical friction is introduced in 1943 by Chandrasekhar. You can find this formula in textbooks. The main idea is that when a perturber moves inside an infinite constant density medium, then there will be a wake behind the perturber, and gravitational interaction between the wake and the perturber will cause a friction. Very simple idea. You know, at least in a constant density medium, it's possible to exactly find the friction. As you see here, mass and the velocity of the perturber is very important, and also there is a function I here, and it for collisionless system or gaseous system, it's different. And for gaseous system, we see that the when velocity of the perturber reaches the sound speed, then the friction will be too much higher than the collisionless case. Existence of this force has several consequences. You know, many consequences has been attributed to dynamical friction. For example, mass segregation in star clusters. I have tried to mention some important papers and original papers. Damping and excitation of galactic warps, sinking satellites in dark matter galaxy halos. This is relevant to the four nights puzzle, in fact. Orbital decay of binary supermassive black holes, destroying the dark matter cusp in spiral galaxies. As you know, existence of cusp in lambda CDM simulations is a serious challenge for lambda CDM. There are many proposals currently, and the main ones are based on adding baryonic feedback to the system. But one of the old proposals to resolve this problem, I mean cusp problem, is to take into account the role of dynamical friction. And the idea is that if there are some fragmentations in the system, and you know, the fragmentations can heat up the cusp and change it to a core, in fact. The other consequence, which is interesting for us in this study, is the slowing down the galactic bars. Actually, when a stellar bar inside a galaxy rotates inside the halo, then there will be dynamical friction, and we should see that the speed of the halo change with time, decreases with time, in fact. Actually, understanding the bar-halo interaction is not simple, and one needs to use linear and nonlinear resonant dynamics. We know that the main part of angular momentum transfer happens via particles trapped in resonances, and understanding this is not easy, but the upshot is simply that when a bar rotates inside a galaxy, then it will induce a wake behind itself. It has been beautifully shown in this simulation with Weinberg and Katz. This is over density, in fact, density isocurves in dark matter halo, and this white line shows the position angle of the bar, and it rotates counterclockwise, as you see. And this blue region density, and the red region shows the under density regions. So it's natural to expect that there will be a force in bar, and its velocity will decrease in time. So the question is is there any observational evidence for this? Actually, we look at some snapshots for galaxies. We cannot observe the time evolution of the bar, but for more than 20 years, it is well known in the community that we can measure the pattern speed, and also another parameter, we call it R parameter, and they can find the velocity of the bar. Actually, R parameter is the ratio of corrotation radius over the bar length, and it can quantify the speed of the bar. In fact, if this parameter gets smaller than 1.4, then we call the bar a fast bar, and otherwise it will be a slow bar. Here in this figure, as you see, this dotted line shows the border between slow bars and fast bars. As it's completely clear here, all the galaxies studied in this paper, I forgot to say that it's one of the most recent observations of R parameter. In this paper, authors has tried to remove all the sources of errors, and it's a reliable observation, but it's very well known. As I said, it's old, and for 20 years, people know that all observed galaxies has fast stellar bars. Okay, and so what's the problem? The problem is that when we use in isolated and controlled simulations in dark matter models or in cosmological simulations, then almost all the galaxies host slow bars. There is a big tension. Here we have brought this picture from Eagle's cosmological simulations, and this error bars shows real observations, and this red points belongs to simulations. Then, as you see, all the bars observed in Eagle simulations lies in the slow bar regime, and all the observations in the fast bar regime. Dynamical friction is the main reason for this. There are many proposals currently, and people are trying to propose some particles, more exotic particles, to remove the dynamical friction. In fact, and I'm not going through details of them. And instead of talking about that proposals, I'm going to talk about less interesting proposals, in fact, in the community. And as you know, one can assume that there is no dark matter and try to change the dynamics or gravity. The most important and famous theory in this sense is Mond, and which I'm not talking about Mond here. I will talk about non-local gravity and also MOG. Two theory, they are similar in the weak field limit, they are similar to each other. But non-local gravity, please remember, yesterday we had a talk by Kumars Karami, who provided us with a short but very informative comparison between teleparallel gravity and general relativity. And I can say that non-local gravity is in fact, is a non-local version of teleparallel gravity. I'm not writing the field equations here, but it's interesting to say that in parallel formalism, when we use Weizenbach geometry, then equations of motion of general relativity gets very similar to electrodynamics. It's strange, in fact, but the main idea in this theory proposed by Hale and Mashhad is that if you start with teleparallel gravity, you are dealing with equations which are very similar to electrodynamics, then it would be easy to add non-local effects. This is the idea. So eventually there are some complicated field equations, but in the weak field limit, which is relevant to our problem, I mean with bars and galactic dynamics, we need only the weak field limit. Non-local features, non-local effects ultimately appears as a non-local term in the Poisson equation. And this term here, you can look at this as an effective density, and this effective density is claimed to help to handle the dark matter and other related problems. And as you see, this equation can be solved, and the gravitational fields takes this form. There are a Yukawa term here and two free parameters. And these free parameters has been obtained by Rahvar and Mashhad using rich, in fact, data of rotation curves. Okay, the other theory is Mach. It is a scalar tensor vector theory. It has two scalars, complicated theory. And in the weak field limit, again, it lead to this Poisson equation. There is another correction term here. Again, there is a Yukawa-like correction, and very similar to non-local gravity. It also has two free parameters, and using rotation curves, we find them. And we use the same parameters in our simulations. So what about dynamical friction? Recently, we have found some exact solutions, relations for dynamical friction in non-local gravity. The main idea is that in theories which try to handle or resolve the dark matter problem, the gravity should be stronger. We need a stronger gravity to raise the rotation curve without any need to dark matter particles. So it's completely natural to expect that dynamical friction should be stronger, because dynamical friction is nothing but a gravitational force. So dynamical friction should be stronger in modified gravity theories. Then it's natural to expect that we should see more slower bars in galactic scales, right? But one need to be very careful when using these expressions. As you see here, we have an extra correction term, and delta is positive here, and it depends on free parameters of the theory, and also the length scale of the baryonic system. When we use a typical value for D parameter, typical value for a galaxy, I mean, and then we see that this friction can be 10 times stronger than Newtonian gravity, but the main point is that here, every parameter, every quantity you see here, like rho naught, like R max, R mean, all the parameters here belong to baryonic matter. They are different from Dark matter case. In dark matter case, when we want to use this equation, then it's necessary to use the dark matter density here. But in non-local gravity, we need to put only baryonic matter density here. And in general, overallly, the result is that dynamical friction should be weaker in modified gravity, at least in non-local gravity. The other point is that it's not easy, it's not correct, in fact, to use this equation for a bar. Finding an exact expression for dynamical friction is not easy, and this is only for a point mass moving inside a constant density medium. So there's no way to check the in fact, this result analytically, and we need to use n-body simulations. For this aim, we use Galaxy code. This code has been written by Jerry Selwood, and it's a sophisticated code, and it includes every mass component for disks and halo. We have changed the kernels, what we have added the Yukawa corrections which appear in modified gravity models. And we have tested everything to make sure that the convergency and other things, energy conservations and other things. Then we make some initial galaxies, numeric galaxies, for example, we construct a model in modified gravity and another one in dark matter model. The baryonic distribution of these two models are completely similar. We use the same Toomre parameter, we use the same dispersion velocity, everything is similar. Okay, and the main problem is that one of them has Yukawa corrections, the gravitational force is different, and the other one has a halo. Then we release these models and observe the evolution. So here for exponential disks in modified gravity, this plot shows the initial rotation curve. In fact, this blue curve belongs to non-local gravity. This dashed curve belongs to MOG, and the solid black curve belongs to dark matter halo, in which we have a Plummer live halo. With live, I mean we have a halo from particles. It can be rigid, but to see the dynamical friction impact, we need to use live halos constructed with particles. I forgot to say that we use all the parameters, the length scales, smoothing parameter, masses, and everything. Similar to real galaxies, we use typical values for them. So this is a snapshot for a Mondian simulation. It's I have brought it here just to show that how our simulations look like. Can I share my screen to show an animation?
Yes, I think, but sorry. Yes, I think, but I think that your time is limited, so you have only 1 or 2 minutes.
Okay, thank you. I'll skip this. Okay, here we see the bar amplitude. It's relevant to the bar instability in different models. And here, top panel belongs to, in different panels, we use a different number of particles. And as you see, by bar amplitude, I mean the second coefficient of Fourier decomposition of surface density, in fact. And as you see, bar instability happens more quickly in non-local gravity, and there are some oscillations in modified gravity models. Please also see this dashed curve. And in the dark matter case, there are not rapid oscillations, but the main difference is that in the end of simulations, we see stronger bars in dark matter halo cases, right? And modified gravity leads to weaker bars. Now, I think that follow-up work is required to see which one is consistent with observations. The other important quantity is pattern speed. This is completely relevant to the dynamical friction. And as you see, and as we expected, in fact, dynamical friction causes the pattern speed to decrease in dark matter case. This decline is directly related to dynamical friction. And in modified gravity cases, you see it's almost constant. There is no rapid decline in pattern speed, but still we see some oscillations. In fact, we can find the origin of these oscillations when we look at the spectrum of the simulations. Then we realize that there are several density waves propagating in the surface of the disk in modified gravity models. It seems that in dark matter models, when we have a dark matter halo, then it can suppress local scale perturbations, but it's not the case in a modified gravity case. So another important point is that to check if our results depends on the initial mass functions. I mean, initial mass profiles. We have used only Plummer sphere and exponential disk. Then the question was, if we use another density profiles, then the results may change. So recently we have studied Kazmin Tumre disk, and also for halo we have implemented isothermal and Hernquist halos, and NFW, Frank Navarro halo. And as I will show here, nothing changes, and it seems that the difference between modified gravity and halo doesn't depend to the mass components, initial mass components. Here, this is the initial rotation curve again, and LIH means an isothermal halo, Plummer halo, NLG and MOG, and LHH here means live Hernquist halo. As expected, here we see a rapid increase in the rotation curve because Hernquist halo has a cusp. Then it was interesting to see if we put a cusp there, then it would be interesting to see the evolution of stellar bar. So again, this is bar amplitude for bar instability, and we still see that non-local gravity has the most violent instability here. And again, we see that for Kazmin Tumre disk, the bars are weaker in non-local gravity and much stronger in dark matter models. However, as you see here, for Hernquist model, we find a strange behavior. In fact, we couldn't find a final answer, final explanation for it. But if you look at long-term evolution, then we see that the bar grows in LHH model, and eventually it will lead to stronger bars. It's still different from modified gravity models. But we see that there is a long interval of time here in which dynamical friction doesn't operate. I know it's strange, and now I'm trying to say some words about it. Before that, here, these are some snapshots from the disk in the end of simulations. Even with your eye, you can discriminate that stronger in dark matter cases. These two top panels belong to dark matter models, Hernquist and isothermal model. And here, these two panels belong to modified gravity. For pattern speed, again, as expected, we see that dynamical friction doesn't operate in modified gravity, but very seriously changing everything in in dark matter cases. But here for Hernquist model, as I mentioned, there is a long interval in which dynamical friction doesn't, it's in fact it disappears. We have a similar thing, similar thing in the literature. We call it core stalling effect. It's very interesting that if a particle move on a circular orbit inside a constant density core, inside a core, then dynamical friction disappears. And the simple explanation would be if a perturber moves inside a constant density core, then small particles fall into epicycle motion around the perturber. And in epicycle motion, which is a periodic motion, there will not be any net angular momentum transfer. And so dynamical friction disappears, and there will not be any decay in the orbit of the particle. This is an old idea proposed to solve the Fornax puzzle, to solve the orbital decay of Fornax globular clusters. But the problem there is that there isn't such a core in Fornax to expect such a behavior. But as you see here in the Hernquist model, after with a time unit, each time unit in our simulations indicate 10 megayear. And after this time, 600 units, we see that then the pattern speed starts to decline. Here in this zoom panel, you see clearly that eventually dynamical friction gets important also for Hernquist model. It's very interesting that, as you remember, we have a cusp here, and in this panel, we have plotted the density of the halo here, with time. This black curves belong to Hernquist model, and this gray curve belongs to Plummer model. As you see, nothing serious happens in Plummer model. Plummer has a core inside it, but for Hernquist model, we see that there is a cusp, and then this cusp gets flattened here, and in fact we can say that the activity of bar inside the halo will destroy the cusp, and then we totally have the cusp destroyed. Then again the dynamical friction starts to work more seriously. Another point is that, as we saw here, here in bar amplitude, we see that Hernquist model has a weak bar, at least in this interval. Weak bar means that there is a bulge-like thing, and not a bar. And when you have a rotating bulge, there shouldn't be a substantial amount of the dynamical friction for a rotating body, and we need a mass body to move inside a medium to see dynamical friction. How much time do I have?
You have 5 minutes.
Okay. This is our final result. As I said, to compare simulation results with observations, we need to measure the R parameter, the ratio of correlation radius over bar length. There are some difficulties. Even in simulations, to find a bar length, we have some difficulties. For example, as I said, there are some oscillations in modified gravity models, and this oscillation causes some wrong estimation for the bar length. When we look carefully, there are other modes, and there are some spiral small scale waves, and they they cause some artifacts, and one need to be very careful when measuring the bar lengths, even in observations, even in simulations. Okay, and here, as you see, for Plummer halo, we see that Let me mention that these two lines here, these dashed lines, this area is the fast bar regime. You know, observations lies in this regime. And in our dark matter model, we see that the bar starts with, you know, it's slow in the beginning, and it remains slow during the whole simulation time. Here, this blue color belongs to NLG, non-local gravity, and we see that it's almost fast, compatible with observations, in fact. For MOG, it happens also. We see that it's also fast. For isothermal halo, this is in fact non-singular isothermal halo. You know, we have two types of isothermal halos. And again, we see that the bar is fast, and also for Hernquist case. Therefore, there is a clear difference between modified gravity models. Recently, we have a paper, we have another work in which we have clearly shown that the MOND also leads to fast bars and consistent with observations. This clear difference between these two different viewpoints is directly relevant to dynamical friction. So it seems as a key concept. And my last point, of course, one cannot, just use these R parameter to claim that modified gravity works better. There are many other things to be checked. Here, this is the edge-on view of our simulations. These top panels belong to dark matter models, and bottom panels to modified gravity models. As you see in dark matter models, there are X shape and peanut shapes. As far as I know, these are very familiar and in real galaxies. But in modified gravity models, in MOG, we have a warp. We see a warp in our simulations, and in non-local gravity, we see a thick disk in the end of simulation. You know, and it seems completely different morphology. You know, there are serious differences, and as I said, it seems a wide follow-up work is required to find reliable results in this sense. I mean, comparing modified gravity and dark matter models. We've seen in our simulations that disks are much more extended in modified gravities. I mean, in radial size, they are much more extended in dark matter cases. And we believe that this big differences, you know, there should be some link with real observations. So this is my summary and conclusion. Dynamical friction has serious impact on the evolution of stellar bars. Dynamical friction doesn't operate. Maybe it's better to say it's very small and weak in modified gravity models, and bar instability happens more rapidly in non-local gravity. In our modified gravity models, we reach to weaker bars. We know that in observations there are strong bars. And maybe the main point regarding the dynamical friction effect, we can say that modified gravity leads to faster bars compared to dark matter models. Thank you very much.
Thank you very much, Mahmoud, for a very interesting talk. I think that you already have one question here from Wahid Amiri. Wahid, could you please turn on your microphone?
Hi, Mahmoud. Thank you for your talk.
Thank you.
I have a basic and somehow simple question regarding the non-local gravity. What is the main difference between the non-local gravity and MOG or other models of modified gravity in terms of studying external field effect?
Good question. You know, you cannot even compare these two theories. You know, they are completely different. For example, in non-local gravity, there isn't any new field. You don't have any new field, okay? But in MOG, we have 3 extra fields, 1 vector field and Proca vector field and 2 scalar fields. You know, from this sense, they are completely different. And you can say Mach is a local theory. There isn't non-local effects as those appears in non-local gravity. Completely different, okay? But about external effect, I worry if external effect exists in non-local gravity. I know that this effect is very important in MOND, but I don't think that such a behavior exists in non-local gravity or in MOG. Maybe in MOG, it's better to look for some other mechanisms like chameleon mechanisms or something like this. But I think that there isn't such an external field effect in MOG or even in non-local gravity. The other point is that non-local gravity leads to very complicated equations, because you in your equations in cosmology or in astrophysics, you need the past history of your system. The current situation, the current dynamics of the system depends on the past history, and it's not the case in MOG. So they are totally different, and for external field effect, I think that there shouldn't be.
Thank you.
Okay, I think Hossein has a question, so please go ahead.
Yes, thank you very much, Mahmoud. Actually, I have two comments instead of question.
Yep.
One is regarding the mass the list of the consequence of mass segregation. I think it is. I would add the formation of dark subsystem, black hole subsystem. This is also the consequence of the mass segregation, which is, it can be interpreted as IMBH, for example. Okay. Because of mass segregation, the subsystem of black hole is formed in star clusters. It is confirmed by simulation, but not yet by observation. And also, I think you got very interesting results and shows the difference, for example, for the morphology of disk in different gravity models. So I think it would be a good next step to compare with observation, because we have enough observation about the morphology of disks, so it is easy to compare, I think, for the next step.
Yes, of course, we are working on it.
Yeah, and also I think it is interesting if you compare your results with MOND, dynamical friction in MOND. We have some results by Nipoti, published a decade ago, but we have also some results by my student, Shahriar Motamedi. It is not published yet, but we can send you, how much the difference in the dynamical friction in MOND, and we calculate the merger rate of galaxies, for example.
Very important.
So, you found dynamical friction is 10 times stronger in the, for example, the Mashhad model. So it is interesting to compare with MOND results.
For Mondian simulations, we have submitted papers, in fact, with Pavel's team. We have compared all modified gravities with each other, and specifically with MOND. And it's very interesting that these models, all of these modified gravity models, work in the same way. There isn't a serious difference between MOND and other theories. And about the merging rate, I have a comment. As I said, in non-local gravity, we see in a similar situation. If you assume that particle moves inside a medium with density similar in non-local gravity and in Newtonian gravity, then you will see a stronger dynamical friction in non-local gravity. Okay, but in situations which matter for us, the dynamical friction is weaker, because we need to put baryonic mass components and information in our equation, in dynamical friction, and not the dark matter one. And so my main message in this talk is that dynamical friction is weaker and not stronger. And so for merging rate, we would expect, lower rate in non-local gravity compared to a standard case.
Okay, thank you very much. I think that there is another question by Moin. Moin, can you please turn your speaker on? Moin? Do you hear me?
Can you hear me?
Yes.
Yeah.
Okay, thank you. Thank you, Mahmoud, for your nice talk. I really enjoyed. I have a question about the bulge formation. I think I didn't get how you distinguish between the bar and the bulge. And the bulges are also very important. I don't know how you manage that. And especially the bulge formation might be related to the funneling of the gas into the galaxy in different ways. Not the main one. But any instability in the disk, for example, because of any, for example, satellite galaxy or anything else. I mean, there are many different aspects of the formation of the bar and the bulges, and you look into that with a secular evolution, I think. But in general, I think the bulge formation should be considered at first because that's observational is more interesting and more comparable, and then we go to the bars. I don't know if you have any comments on that.
Yeah, thank you. Very pertinent comment, in fact. We have a very clear and straightforward definition for the bar. We measure the second coefficient in surface density, Fourier coefficient. This coefficient is 0 for a bulge, for a spherical bulge, I mean. And so if it's non-zero, and we're comparing to the other modes, then we decide that there is an oval shape, as you saw in this. Let me show this figure here. We deal with such configurations, and we call them bar because of the reason that I said. We do not call them bulge, but I completely agree with you that it's necessary even to put a bulge. More sophisticated simulations should start with a bulge. In initial conditions, we need to put a bulge. And as you know, spherical bulge induce some stabilizing effects, and it can change everything, But since our main purpose is to study the bar and its evolution, we have not put bulges. And actually, we have some simulations done in modified gravity with bulge. And as you mentioned, there are serious differences in that.
Thank you very much. We're running out of time. Thank you, Mahmoud, again. Change